All right, this is the forces video. So the original question was, how fast are you moving right now? And this is what was explored in this lab, the How Fast Are You Moving Right Now lab. So in the first part of this lab, there's research into how fast humans can move on Earth. So walking, the average walking pace is 1.4 meters per second. Now the fastest runner is Usain Bolt, and when he ran that world record-setting pace, he topped out at 12.4 meters per second. That's about 28 miles per hour. Now, the fastest car in the world can go 148 meters per second. That's about 331 miles per hour. Now, with trains, the fastest train in the world can go 119.5 meters per second. That's 267 miles per hour. Now, the fastest plane is the Blackbird. Now, the Blackbird can go 972.2 meters per second. That's about Mach 2.8, so 2.8 times the speed of sound. And the fastest human beings that have ever traveled were the astronauts aboard the Apollo 10 mission, and they went 11,082.5 meters per second. That's 32 times the speed of sound. Now, then you were asked to research how fast you were moving right now. Well, if you're just standing still in this room, well, relative to this room, you're not moving, 0 meters per second. Now, the room is in Indianapolis on the planet Earth, which is rotating about its axis. Relative to Earth's axis, how fast are you moving right now? You're going to have to find that latitude, and it's 361 meters per second. Because if you're on the North Pole or South Pole, you're really not moving relative. You're just sort of spinning around. If you're at the equator, you're going much further. And based on where we are, you're going about 361 meters per second, 807 miles per hour. Now, the Earth is revolving around the Sun as well. Relative to the Sun, how fast you're moving? 29,952 meters per second. That's 19 miles per second. Now, the solar system is also revolving around the supermassive black hole Sagittarius A star at the center of our galaxy, the Milky Way. Relative to Sagittarius A star, how fast you're moving? 229,779 meters per second. So that's 143 miles per second. Now, the galaxy is also moving towards what we call the Great Attractor. Now, relative to the Great Attractor, you're moving 600,000 meters per second. That's 373 miles per second. Now, the Milky Way is also moving with respect to the cosmic background radiation. Relative to the cosmic background radiation, how fast are you moving? 611,111 meters per second. And the speed limit to the universe is the speed of light in a vacuum. That's 299,792,458 meters per second. That's essentially going from Earth to the moon in 1 second. Now, all of these numbers were graphed, right? So that first graph is going to be the speed of humans on Earth, and then this next graph is the speed of Earth in the universe, and then the last one compares all of it to the speed of light. So if you look at the speed of Earth in the universe graph, you'll notice that, well, Earth is traveling incredibly fast through the universe, right? Whether it's around the black hole, whether it's the Milky Way traveling, compared to humans. The fastest humans, Apollo 10, you can see there's just a tiny little bar on that chart, the speed of the universe chart. So we're moving incredibly fast through the universe with respect to other objects. Now look at the speed of light graph. Now you'll notice that even the fastest that you could relatively say that Earth is going with respect to the cosmic background radiation, it's nothing compared to the speed of light. So let's look at these conclusion questions. So you've just researched and concluded that you on Earth are spinning and traveling through space incredibly fast. Do you feel this motion? So you're not going to feel this motion, and it's because everything is traveling with us, right? So, like, if you're sitting in a chair, that chair is also going around the sun at 19 miles per second. Same thing with, like, the books that you're holding, or everything around us is traveling with us. So we don't really feel that motion. We don't notice the motion. Even the air around us, even though we're going around Earth, we're rotating at 800 miles per hour. We don't feel that because the air is also going with us. We don't feel that motion. Now, in all the questions where you're researching speed of Earth through the universe, what did you need in order to answer all of them? Well, you needed a frame of reference. That was what this lab was about. You needed a frame of reference. And it always asked relative to, like, the sun, how fast are you moving? Relative to Sagittarius A star, how fast are you moving? Relative to the cosmic background radiation, you always needed that. Now, in all the questions where you're researching the speed of humans on Earth, well, why do you think a frame of reference didn't need to be established? Well, think about it this way. If you're in a car and that speedometer says you're going 30 miles per hour, well, that's 30 miles per hour relative to what? Well, it's going to be the surface of the Earth, right? The most common frame of reference is the surface of the Earth around us and stationary things attached to us. So If somebody's running and you say you're going 10 miles per hour, well, that's that's relative to the Earth's surface. So when we're here on Earth, we just use the surface of the Earth as our fixed point. But like you researched in this lab, well, a fixed point is also relative because like Earth is also moving incredibly fast through the universe. And the last question is, how fast are you moving right now? And explain your answer. Well, it's impossible to say or answer this question without a reference, without a frame of reference. You need to how fast you're moving right now relative to this room is going to be different than how fast you're moving right now relative to the background radiation. It's going to be different. So you need a frame of reference. So us look at some of Galileo's assumptions. So let's just look at this thought experiment. So let's just say you're on a train going 100 miles per hour, right? And you fire a bow and arrow, and that arrow goes 200 miles per hour. Well, if somebody's on the ground, they would measure that arrow going 300 miles per hour. Now, you would measure that arrow going 200 miles per hour. So, and if you fire that same bow and arrow on the ground, it would go 200 miles per hour. So, yeah, we would get different measurements. Like I would read from the train 200 miles per hour on the ground. You would measure 300 miles per hour. Those velocities add. So, based on these observations, Galileo made a few assumptions. Number one, velocities add together in space and time don't depend on velocity. So, this brings us to another question. Could you increase the speed of light? Well, let's look at this a little bit differently. Let's just say that same person is on the train and they fire like a laser beam at a target. Well, the speed of light in a vacuum is that was researched in that lab, 299,792,458 meters per second. Now, let's just say you're going on a train at 100 kilometers per hour and you turn on that laser beam going at that speed of light. Well, when you measure it from the ground, that beam isn't going to go any faster because the speed of light, that is the speed limit to the universe. So that laser beam isn't going to travel. Now, if you measured it from the train, you would get the same speed as the person measuring it from the ground, even though you're moving. So the weird thing about this scenario is that the beam of light will always be traveling the speed of light no matter what perspective the measurement is taken from. Now, how is this possible? This causes some issues. Now, Newtonian physics and Maxwell's equations break down at fast speeds, close to half the speed of light. You'll notice over there, like, yeah, close to the speed of light, some things start to break down. Now, it was Einstein who asked two simple questions. Number one, well, why is it the speed of light is the same for all observers? And why can't I accelerate to the speed of light and watch light travel? So, in 1905, Einstein came up with his theory of special relativity, and that explained that the laws of physics are the same for all non accelerating observers. And it showed that the speed of light within a vacuum is the same no matter the speed at which the observer travels. So, this is Einstein's theory of special relativity. Number one, time is the fourth dimension that we travel through. The faster you move through space, the slower you move through time. Light doesn't experience time. So, why don't we notice these effects then? Why is it that if I'm moving, why don't I notice that time's slowing down? Well, like you've already determined in this lab, well, we on Earth and relative to the speed of light are traveling about the same. Everything around us traveling about the same speed. Nothing's really going close to the speed of light around us. Even the fastest humans right now on the International Space Station traveling at 4.76 miles per second are only traveling 0.002% the speed of light. So the example that I use is Scott Kelly, that's the astronaut on the right, is an astronaut who spent a year aboard the International Space Station traveling at 4.76 miles per second. Now, Scott Kelly has an identical twin brother named Mark Kelly who stayed on Earth. Now, to quote the older twin, Mark Kelly, he said, so whereas I used to be just 6 minutes older, now I'm 6 minutes and 5 milliseconds older. Now, because Scott Kelly was moving a lot faster relative to Mark, well, time slowed down for him. Now he didn't notice this time. Like if you're going incredibly fast, even close to the speed of light, and on a spaceship, you're not slowing down. What happens is that you just have your time frame, your frame of reference is different from everybody else. So that's why we don't notice it because everything around us is moving relatively the same speed when you compare it to the speed of light. Even the fastest human beings that are traveling right now, which are on the International Space Station. So, why do you need to know this for a physics class? Well, the theory of special relativity established two things, right? In physics term, there is no difference between being at rest and moving at a constant velocity. And acceleration is the only absolute or real motion. So these are some final thoughts. Remember, there's just too much unknown in the universe to take a break from learning. Get out there and question everything.